Good morning, and welcome to Ask the Experts. I'm Samantha Pelham, a Media Relations Specialist at Ohio University, and your moderator for today's conversation. Today, I'm speaking with two experts who I'm sure have been quite busy as the summer storms pick up. Ryan Fogt, Professor of Meteorology in the College of Arts and Sciences and Director of the Scalia Lab for Atmospheric Analysis, and Jana Houser, Professor of Meteorology in the College of Arts and Sciences. Welcome, and thank you both so much for taking time out of, I can only imagine, your extremely busy schedules to virtually sit down and talk with me today on this topic that impacts literally everyone all over the globe, not only during the peak of summer, but also all year long. Between the extreme high temps that we've been seeing in the Pacific Northwest to Tropical Storm Elsa, who's making landfall, I want to say currently, or maybe just did, and, the overall severe weather that's been popping up around the country, I feel like we have a lot to talk about this morning. But before we get started, if each of you could please introduce yourself and your area of expertise, that would be great. Ryan, how about we start with you?
Hi, Samantha, and thanks for having me. So I'm a professor in the geography department here at Ohio University. My area of research is on climate a little bit more than meteorology. I'm particularly interested in the climate of Antarctica and understanding how climate down there is changing and what roles human activity is playing in that change through climate change, but also what roles natural variability is playing in that change. I teach classes ranging from intro meteorology all the way up through dynamic meteorology, which is the most math-intensive course that we have in our major. And I also work in the Office of Sustainability on campus. I serve as the Sustainable Administration Hub Coordinator and bridge my climate interests with sustainability over there and engage students on campus to work to improve targets on our sustainability plan.
Great, thank you. Yeah, you're definitely a busy man who is doing a lot for both, sustainability, the environment, and climate. And so we thank you for all of the work you've been doing. Jana, how about you?
Yeah, hi, Sam. Thanks for having us both. This is really fun. I'm Dr. Jana Houser, and as my title basically follows suit with Ryan's, I'm an associate professor of meteorology in the College of Arts and Sciences geography department. And yeah, my area of expertise is severe weather and particularly tornadoes. So my research uses observations from mobile radars to examine thunderstorms and tornadoes that are produced from supercell thunderstorms, with a particular emphasis on the evolution of rotation within tornadoes as they form and as they decay. And then I also am funded by the National Science Foundation to investigate how tornadoes interact with the physical ground surface below. So we're talking about hills and valleys and different types of land cover and so forth. I teach a wide variety of courses as well, including anything from the introductory classes and then the synoptic and mesoscale meteorology classes, which are kind of like the small scale versus large scale weather patterns courses that we teach for our majors. And then I'm also teaching a radar course and have a couple other specialty courses along the way as well.
That's great. Thank you. And, I'm really fortunate that we could have you sit down and talk with us today and that you're not tornado chasing right now because, I know the summer is a good time for you to go out and do all of that. So thank you both again. It is really appreciated. For our viewers, if you have any questions for our experts about severe weather or the correlation of climate change with weather, climate in general, or just general weather questions, please drop those questions in the comments section of the live stream, or feel free to direct message your questions to the Ohio University social media channels. We will do our absolute best to get to as many of your questions live stream. And if we don't get to them, please know that we will still send them along to our experts so that they can answer them for you. So without further ado, let's get our conversation started. Ryan, I will go ahead and ask you the first question. Can you talk a little bit about how your research, the connection with your research when it comes to weather extremes and climate change?
Yeah, so I look at Antarctica, and Antarctica is the place of extremes. If you like extreme weather, maybe not tornadoes, on Earth, both confirmed by measurements and satellites. It's one of the strongest places for winds that are non-hurricane related winds, sustained. It's the highest continent on the Earth, and so it has these extreme conditions, which make it virtually uninhabitable. You can't reside there in the interior of the continent safely for a long period of time. They have bases where they do research, but even then staff rotates in and out of those bases periodically. So, I'm looking at how did the degrees change in Antarctica? And particularly right now, my project is on the sea ice that surrounds Antarctica. And it was a really interesting puzzle because in 1979 to 2016, sea ice around Antarctica was actually increasing. And that's in stark contrast to what we've seen in the Arctic Ocean, where we've seen really rapid decline in sea ice extent. And that was puzzling. And then along came 2016, and the sea ice plummeted in Antarctica and went down really low and stayed that way for about 4 years. And then 2020, in the midst of the pandemic, sea ice came back and rebounded, and it was close to average again. And so this huge change from near record values in the sea ice down to nothing and almost nothing in 2016, and then rebounding to near normal again in 2020 shows that there's rapid change that can happen in the Antarctic continent that we just don't fully understand because observation records are really short. And so my goal is to provide a longer history of Antarctic climate through reconstructions and use those reconstructions to help us understand how these changes are happening, how unique they are in a longer context, and how they might happen in the future.
Wow, that's great. I honestly didn't know half of that information about Antarctica, and so it's really interesting to find out how extreme the weather really is, especially considering that it is, like you said, uninhabitable, and that we personally don't get a chance to see it very often unless we have researchers like yourself who are studying it and presenting it to us.
It's a fantastic place. It's I've been fortunate to be down to the ice 3 times. And there's something that they call, when you land on the ice for your first time, it's this experience of getting ice in the veins is what they call it, because you become hooked. And I'm sure Dr. Houser has the same experience when she saw her first tornado. There's something about it that curates you in this scientific fascination where you are both excited but also really curious. And you want to know more. You see yourself finding more and more questions as you look around. And you want to spend your career answering those questions. And as you answer one question, you learn about 3 other questions that you want to answer too. And so, it's my goal to bring a place that's so remote much closer to home, because even what's going on down in Antarctica has dramatic impacts for the rest of the world. So we may think it's isolated and we're not going to experience anything from Antarctica here, even in the US, but certainly we're seeing those connections. And so it's a place of worthy study because it does influence the whole patterns across the planet.
Thank you. So Jana, like Ryan just said, I'm sure the first time that you went out and got to study tornadoes was such a thrilling experience and something that you've clearly continue to do and have researched throughout your life. So can you talk a little bit about your work with rapid scan radar observations revealed and the evolution of tornadoes as they're forming, and a little bit about what you have discovered since researching and studying tornadoes?
Yeah, absolutely. So if you've ever, I'm sure probably our audience has not done this or experienced this, since we do live in Ohio and it's a little bit less frequent, but still occasionally I'll encounter somebody somewhat locally who has experienced a tornado event. But if you've ever seen videos or can sort of imagine in your mind, a tornado is not a particularly long-lived event, right? They occur over relatively short periods of time. And if you've ever watched it, even if it's on a video on YouTube, you can see very, very dramatic changes in the structure and the look of the tornado over very short time periods. So scientifically, one of the things that has been a real major hindrance in our progress in understanding tornadoes has been the inability of our instrumentation to actually keep up with the processes that are occurring in tornadoes. So one of the major areas that I have incorporated as far as observations is to utilize mobile radars that scan very quickly. So we collect data every approximately 20 to 30 seconds in comparison to more traditional radars. Mobile platforms typically have scan times between 1 to 2 minutes. And then the national network of radars that you would see if you just turned on your radar app, that scans the atmosphere in the same comparable spatial area in roughly 4 or 5 minutes. So you can imagine you can have a tornado that basically develops, matures, and decays all within that one time period where you're collecting basically one representative sort of state of the atmosphere from traditional radars. So bringing mobile radars that scan very rapidly into the picture is very important. Mobile is important because we have to take the instrument to the storm, and then rapid because the tornado is occurring on very rapid timescales. So one of the things that I have really been interested in investigating is how tornadoes are evolving, and particularly just as they're beginning to evolve. So we traditionally have this perception of what happens with the funnel cloud when we think about and conceptualize tornado evolution as they're forming. So the funnel cloud we see kind of start high in the cloud, and then it kind of over a period of time, maybe 30 seconds, maybe 1 or 2 minutes, extends down from the cloud and then makes contact with the surface. And at that point, people commonly say, oh, touchdown, we have a tornado and so forth. But what we've actually found with the radar data, which can actually detect air motion that our eye can't physically see, we've found that nearly ubiquitously in almost every single case that we have studied tornadoes with these rapid scanning radar platforms, really strong tornado strength rotation occurs at the ground before it actually occurs higher up in the cloud, or potentially it can happen at the same time. But the temporal evolution, or how things are changing with both time and with height, is such that it's more commonly a bottom-up process, or some kind of a simultaneous intensification over the lowest, 100, 200, 300 meters up to perhaps even a kilometer or a kilometer and a half with a tornado. So the wind field is actually not truly representative of what our eyes see, which is a really kind of interesting sort of paradox. So our eyes actually lead us to believe that things are evolving in a manner differently than what the invisible wind field is actually doing.
Interesting. I've personally never seen a tornado, up front, but I have my fair share watched them on YouTube just out of interest, and I'm sure a lot of people have. But yeah, the evolution of it is something before at least meeting you, I never had thought about before, and thought about from at least my eye viewing it on YouTube, what that actually means. But you're right; they're extremely rapid when it comes, from at least just the videos I've watched. They're not very long. Some of them can show them, as you would say, touching down immediately and then just kind of jumping around, it seems like. So it's interesting to hear how that evolution is something that continues and happens far before we even notice it when we do see it touch down, like you said. So Ryan, kind of going back to you to talk about Antarctica, you had mentioned something in the last answer that you gave that kind of struck me that I wanted to ask about. So you talked about that Antarctica really does impact the rest of the world when it comes to, weather and climate. Can you talk about what those impacts are on the rest of the world?
Yeah, the biggest impacts are through the ocean. The Antarctic ice sheet sits on bedrock, and as that melts and flows out, or as it flows out to the ocean through glaciers, if that glacier were to be melting, it would raise sea level. And we're seeing a dramatic loss of ice from the grounded ice sheet in this area called West Antarctica, and it's melting from below. It's actually worse than what you'd expect. Warmer ocean waters getting up underneath these glaciers and funneling through currents up and underneath them, melting the ice from below. The ice gets too steep, too heavy, and it cracks off and flows into icebergs. And as that ice melts, it raises sea level. And what we're seeing is more of this ice move quicker to the edge of the coast there, rapidly melt and lead to sea level rise. And the concern here is that this will maybe a process that's unstoppable because of the base of where these glaciers are sitting is a bowl. And so water basically can funnel down slope unstoppably into these areas underneath these glaciers, continue to melt them, even if we weren't to warm the world. Yeah, just gravity pulling water down slope, continuing to melt them from below, they become unstable, they crack and break off and raise sea level. And the U.S. East Coast is an area that will be threatened by this more than anywhere else, just because the different ways that gravity pulls on them, the way that it's still rebounding from the last ice age. And so we could see sea level be impacted all across the U.S., the Everglades into the East Coast and even the West Coast from Antarctica. We're also seeing changes in the ocean circulation related to sea ice formation and changes in freshwater output from that. that impact the global ocean circulation and can reach places way up in the northern hemisphere as well. So even though it's clear down here by the South Pole, it has these global impacts primarily through the ocean.
Yeah, most definitely. I mean, that definitely makes sense, especially when you're talking about the sea ice melting and the rise of ocean levels. And yeah, not something I feel like a lot of people can think about on the daily, about the impact of something, we both talked about that very few people have had the chance to actually visit and experience before, but it does really impact the majority, if not all, of the world, regardless of if you're, on the coast or inland.
Right. Just to clarify one thing here, because you made a little error that I want to clarify, because this happens all the time, is that sea ice melting does not influence sea level. So if the Arctic sea ice melting has no contribution to sea level rise, Antarctic sea ice loss has no contribution to sea ice loss or sea level rise, because that ice is already floating on water. And so you can think of it like if you have a glass of ice water and you let the ice melt in that glass, it's not going to overflow the brim when it melts. It's already displaced the volume of water in that. But ice that sits on land, like a glacier, that flows into water and then melts, that adds to sea, because you're adding ice to water. It's like putting more ice cubes in your glass of water. Yeah, eventually that water is going to flow over, right, and melt, even if the ice doesn't melt. And so adding these icebergs that are breaking off from ice that sits on land in West Antarctica is a huge contribution to sea level rise. But ice that's floating on water, like around Antarctic sea ice or the Arctic sea ice in the North Pole, that does not contribute to sea level rise. And it's a common misconception. People think, oh, Arctic sea ice is melting, sea level is rising. Not from that. It's other contributions, Greenland and West Antarctica and glacier melt across North America and other places.
Okay, so thank you. That is like so informative to me. So when talking about it, when referencing, the rise of sea levels, it's not sea ice, but it is the actual ice from glaciers in the land that is coming in.
Yeah, it has to be not on water to begin with. And so it has to move into water some way to raise the water level. Okay,
great. Is there, and maybe I missed it, like a terminology for that type of ice that melts into it instead of sea ice?
Yeah, it's such a subtle thing. It's an ice sheet. Ice sheet sits over land. Ice shelves and sea ice sit over water. And so, glaciologists know this. People like me that study Antarctic know this. But for the common person, you think sea ice, you think ice sheet, you think ice shelf. Those are all ice. Yes, but very different. And they have different ways that they exist. And so ice shelves and sea ice are already floating on water. But ice sheets, those are things that would sit on land and potentially could flow into water.
Wow. So all of our viewers watching, note that, because I have noted it for when I talk in the future. Thank you, Ryan. So we actually have some questions already from our viewers that I'm going to ask you. Let me see. This one looks like it's directed at you, Ryan. It is from Matt on Facebook. He says, "Hi, I'm an alum living in Columbus. Do you study core samples from Antarctica or just the amount of ice?"
That's a great question. So I myself do not work with ice cores. There's a large group of scientists that do a lot of great, fantastic work with ice cores and go down and collect the ice cores and date them to understand Earth's climate history. And that really helps to understand how unique these changes are. My reconstructions are based strictly on observations. One advantage of using observations like I do compared to ice cores is that you can get a larger sample. We have a pretty good distribution of observations across the southern hemisphere that aid me in getting a good sample spatially. Whereas ice cores, that's just one point, and you're kind of representing that one area. Now, of course, we put ice cores all around the continent, but again, you're still representing a small region with that ice core. Another great advantage of observations is that you have better temporal resolution. You can go from 1 month to the next month, easily in observations because you have a lot of data. In ice cores, most of them are going to be 1 year to the next in the top half of the ice core. And then as you get deeper into the ice core, because of compaction, you might not be able to get annual resolution. But the great advantage and the huge reason why people study ice cores is you can go much farther back into time, right? We can go almost back a million years from an ice cores in Antarctica that are drilled to bedrock. And we get a great idea of Earth's climate history and the cycles of ice ages and interglacial periods with these ice cores that we would never get from observations because they're so short in comparison. So, my work looks at some advantages and uses observations, but there's a lot of fantastic work out there that does use ice cores.
Great. Thank you so much for all that information. Jana, let's go back to you and talk a little bit about tornadoes again. Can you talk a little bit about how can terrain and land cover affect tornadoes?
Yeah, sure. So as I mentioned, that's an area where I'm actively pursuing new research right now. And it's a really interesting phenomena because commonly there's sort of this idea that tornadoes can't form in mountainous terrain or in hilly terrain. And some people even have kind of hinted at the idea of like, well, here in southeastern Ohio, it's the mountains that are kind of not allowing us to get tornadoes. But really what I'm finding is that the terrain is really, it can definitely affect tornadoes, as can the land cover itself. So as a tornado moves over a hill or into a valley, that's going to change the direction of winds that's actually entering into the base of the tornado. And what that is going to do is locally change the distribution of the speed and direction of winds as you go up with height immediately above the ground. So it can be very tricky to kind of put a stamp on what the net effect of that is going to end up being. Some instances, there are situations where a tornado will definitely intensify as it's going downhill, for example. But there are other situations where the opposite holds true. So it really depends much more on the configuration of the terrain and the particular feature that the tornado is interacting with, rather than, the specific, if it goes up, it does this. If it goes down, it does this. Another area that I'm interested in and I'm looking at is how differences in land cover. So we're talking about, a tornado going over a wheat field versus a tornado going through a relatively heavily developed land area or perhaps a forest. There's going to be differences in the friction that's associated with those different land covers. So when you have a relatively open area, there's less friction. When you have a more perhaps like forested area, or you're inserting buildings there, that's going to increase the friction in the air movement that's really basically adjacent to the surface, which also happens to be the layer at which tornadoes are ingesting into the actual circulation of the tornado itself. And what has been shown is that there can be structural changes between tornadoes as they're crossing from one type of land cover to another type of land cover. So that can then actually affect the intensity of the tornado, and in some cases it can even potentially cause demise of the tornado as well. So we're just kind of scratching the surface of our understanding of what that actually is looking like in a quantitative sense. But yeah, it's really pretty interesting stuff that we have there. So another, thing that people commonly ask me is like, well, Appalachian areas, hilly areas like we live in, and, in West Virginia and so forth, we don't oftentimes see tornadoes nearly as frequently as areas that are typically more flat. So people tend to think, well, is this a result of the terrain and topography? And the answer to that is partially, but we can't say that the terrain and topography are going to inhibit our potential for tornadoes. More commonly, what happens is that you actually have larger scale environmental changes in the vicinity of those topographic features that create an atmospheric condition that is less conducive for the storms that produce tornadoes even. So in order to get really violent tornadoes, you need to have sort of a certain set of ingredients present in the environment, and commonly, especially over the Appalachians and also over the Rockies, those conditions don't exist. So more fundamentally, it's just a lack of the atmosphere to produce the necessary conditions to have a tornado form in the first place. If those conditions are actually present, there's nothing saying that a tornado can't occur in this mountainous terrain. And in certain instances, there have been documented cases where terrain actually enhances the likelihood of a tornado forming. One of my students right now is investigating the correlation between tornado formation locations and tornado decay locations in comparison to specific areas of terrain and topographic features in the states of Oklahoma and Arkansas. And one of the really interesting things that has come out of his work is that there is a definite spatial correlation with tornado occurrences and a particular topographic feature that runs through the central part of Arkansas that appears to really be oriented in a manner that enhances those ingredients that are necessary to form tornadoes in the first place. So that's kind of a pretty exciting little piece of information.
Great. Well, I'm sorry I missed some of that. I got booted off, but we've been doing this for a year and a half, so we're used to it. But from what I caught, at least, that sounded, I'll have to go back and rewatch your whole answer once this is finished. So I apologize if I ask questions again that you might have already answered. But we have several more questions from viewers who are interested in your thoughts. This is kind of directed at both of you, and you both can talk on it a bit. Elizabeth on Facebook asks, I have been in the Dayton area for 21 years. Over the last 5 years, we have had an increased number of tornadoes. Is this because of climate change?
So I'll jump on that, I guess, since it's a little bit more correlated with my work. Linking tornadoes to climate change is a very challenging thing to do because tornadoes are, as we mentioned, very short-lived, and they're very connected to very localized events and conditions. So one thing that we can say about the links between tornadoes and particularly the atmospheres and conditions that are required to form tornadoes is that, yes, those things are going to be changing in time with climate change, and they are changing with climate change. But the general consensus is that we're going to be seeing increased variability from a year-to-year sense. And we're also seeing sort of increased spatial variability as well. So certain areas might get hammered in certain years, and then, the next year, after a really active year, that area is really quiet. So establishing a direct link between any one specific tornado event and the climate is really kind of improbable, but looking kind of at a larger scale picture, what we can say is the environments that are going to be conducive for producing tornadoes are actually expected to decrease in the future, and at least here in mid-latitudes. And that is because what's required for tornadoes is an environment where you have really warm, moist conditions at the surface, where it gets really cold aloft. So you need this sort of contrast between cold air above and warm, moist air at the surface. And that by itself isn't going to produce a tornado. But you also need what's called wind shear, which is a turning of the winds in direction as well as an increase in speed as you go up with height. So you get this variability between wind speed and direction as you go vertically up in the atmosphere. And that is really the key ingredient that separates an unstable atmosphere that produces a general thunderstorm that you might see on any given summer day versus the type of environment that can produce a tornado. And what we're actually finding is that wind shear is going to, at least according to our climate models, it is going to actually weaken as we go forward in time as a result of the decreasing temperature difference between the poles and the mid-latitudes. So with increasingly warmer temperatures at the poles, you're actually decreasing the change in temperature in the warm months, which is actually not good for tornadoes because it decreases the wind speeds higher up. But on the flip side of that, the days that do have appropriate conditions and do have that strong wind shear have been speculated to be more robust in producing tornadoes. So what is sort of the large scale picture is that the line is going to be relatively flat from the standpoint of total numbers. But what we'll see is an increase in any one given day producing a tornado. You might have instead of having 20 events, let's put it this way. Instead of having 20 days where there are tornadoes, and each of those 20 days produces 5 to 10 tornadoes, we might instead have 10 days that produce tornadoes, but those 10 days are going to produce, 20 tornadoes each. So the numbers work out to be the same, but the outbreak days are going to actually increase in extent and potentially magnitude as well. We will just have fewer of those days.
Wow. Ryan, do you have anything to add to that?
Dr. Houser is just so brilliant. I think that the only thing I can add is that as you move from large-scale climate change down to smaller scales, both, like tornado time scales, how quick they evolve, as Dr. Houser had mentioned, to, the size of these things, a mile or less in many cases, the connection becomes more dubious between climate and these severe weather events, partly because, greenhouse gases that are the dominant cause of climate change operate on very long time scales, very large spatial scales. And these storms have, as Dr. Houser mentioned, very fine ingredients that are, some of them broad, some of them are very local. And that connection between climate and weather, as you get smaller and smaller scale, becomes harder to establish. But I think there are clear links in many parameters, but all those parameters have to kind of come together in the right way. And some of them are changing in favorable ways, some of them in not favorable ways. So it's really hard to establish that connection.
Great, thank you. And then kind of correlated, and I want to ask this question now. It's from another user who's watching, Matt from Facebook, because I feel like you might have already just in your answer explained this, but maybe it's different. So I want to be able to offer this opportunity for you. Matt asks, for Professor Houser, it's been a down year for tornadoes, but still seeing heat and drought out west. Did the change in human behavior due to COVID affect tornado development?
That's a really good question, but I'm going to say probably not. The specific link between human behavior and COVID is that, we stayed in more, there was less carbon dioxide emissions and so forth. But I don't know, maybe Dr. Fogt can correct me on this as far as, the trend in temperatures in, this year versus previous years, but we're not seeing a direct effect in a temperature sense of our relative reduction of greenhouse gases during particularly, the lockdowns that we saw during COVID. It has much more, tornado occurrence on any one given year has much more to do with these sort of mid-range to global circulations. For example, the El Niño Southern Oscillation is tied with tornado occurrences in some cases, as well as some other climate modulating phenomena as well. So this year was actually initially back in April and March, people were really excited thinking this was going to be a really busy, active tornado season because we were in this sort of La Nina phase, which is oftentimes associated with really highly active tornado seasons. But there's also, as this user mentioned, there's drought going on too, and drought also affects tornado events, especially in the central United States. There's as you can imagine, a feedback that goes on between the soil moisture content and the available moisture in the lower atmosphere and the ability of the atmosphere to even produce a thunderstorm to begin with. And obviously we need a thunderstorm to generate a tornado. So in years where there is drought, particularly in the western and sort of central United States, there also tends to be a reduced number of tornadoes in those areas. And climatologically, the central part of the United States, this time of year, is really kind of the hot spot for tornado formation to begin with, because it's where all of these various different necessary ingredients kind of amalgamate and come together. And nowhere else on Earth does that actually happen. So I would not directly link our behaviors during COVID with a relative reduction in tornado events for this particular year.
Brian, would you like to comment on that?
Yeah, no,
just in
I
climate
think,
in general.
Unfortunately, I don't think COVID's going to solve our climate change problems. The greenhouse gases did slightly decrease, mostly in the transportation sector because we're driving less and flying a lot less. And so there is that benefit. But, from year to year, short-term timescales like that, the changing greenhouse gases is primarily driven by the biosphere and not so much greenhouse gas emissions from combustion, fossil fuel use, and those sorts of things. The long-term trend absolutely is driven by fossil fuel use. And so we're adding more bricks essentially to the pile, as my colleague, Dr. Catherine Cahill says. It's just, adding more bricks. And as you add more bricks, the pile gets bigger. And so that's why we're seeing this upward trend. But, the biosphere really is a big source and sink of greenhouse gas emissions. And so this short-term kind of thing gets lost a little bit. And indeed, June 2021, this last month, was the warmest year on record for the Northern Hemisphere, right? Fourth warmest June on record for the whole world. So it wasn't slowed down or stopped at all because of reduced emissions slightly during the COVID pandemic.
So speaking about these high temperatures that you just mentioned too, can you talk about how, recently the Pacific Northwest has had these persistent record high temperatures? And I know not just them, a lot of places, but we've really noticed them there. Can you talk about what has been causing these and how unique are they? And if there is, you mentioned a little bit the connection to climate change, but if there is like a big connection to it.
Yeah. So this has been a really interesting event at the end of June. They had high records in Seattle and in Portland, many days, 3 days in a row that were above 100 for those cities, which, here in Ohio, 100. But for the Pacific Northwest, they're higher latitude. They're by the oceans. You think they'd be more controlled, and that higher 100 degrees is exceptional. It's really, really warm. Even above 90 in those cities is quite warm. And then you move up into Vancouver, into British Columbia. You also had records in the city, Litson in Canada, set not only city records, but countrywide records for Canada in June. Topped over 120 degrees Fahrenheit in that city. And then unfortunately, they had a wildfire that came through it and also did a lot of devastation related to really high temperatures and drought and dry conditions that was there. These were caused by a ridge of high pressure, really clear skies allowed a lot of sunlight in, you have high heating, but also low south, that would be rapid mountains. Just really led to excessive heat. Okay. Now, in connection to climate change, these temperatures were so extreme, they were records, they were so large that preliminary work on this, suggesting that it would be virtually impossible to have such high record value without long-term climate change. And so this is just a bump above, what climate change is doing. Average across the U.S., we've seen warming of about 1.8 degrees Fahrenheit over the last century. Alaska's a lot more than that. But that warming trend, coupled with just the perfect atmospheric conditions, led to these excessive events. So they wouldn't have been as high without climate change. So we do think there's an underlying contributing factor to climate change. And of course, future work is going to establish that more clearly. But it's virtually impossible that these high extremes would have occurred without the context of this upward trend of climate change.
All right, thank you. And then we have another question from a user who's currently watching. Nate on Facebook asks, with 65 Fahrenheit and 18.3 Celsius, observation at Esperanza in 2020 recently verified by the WMO, what chatter have you seen amongst your peers regarding its significance?
Yeah, Esperanza, they were the previous record, not on they're slightly off. Well, they're on the Antarctic Peninsula, so they're a little bit farther north. They're not on the ice sheet. Excuse me, like South Pole or Russian station Vostok. So they're a little bit farther north, but this one was a really large event. It's related to kind of conditions that happened in the Pacific Northwest. You had a dome of high pressure, really strong ridge, and flow over by a mountain range and flow over the mountain and coming down into this base. It's not a city, it's more like a base, a research base, and flow coming down. And as that flow comes down a slope, it gets pushed, the weight of the atmosphere above it pushes it down and warms it. And that causes it to get even warmer. And that flow coming down was really particularly strong that day. So it added onto the warming that we're seeing, naturally it happens in February, that's their summer. And so on top of that, warming and the climate change signal added to this huge record event. And so, it was a big event, just recently verified by the WMO, published in the American Meteorological Society, Bulletin of the American Meteorological Society. So it's impressive, but in some ways expected. And I hate to say that because it just makes it kind of feel like I'm committing to the fact that we're going to see more and more of these reestablished, not only in Antarctica, but like we're seeing. Unless something happens with gas emission, climate change, we're going to see high record of outpace cold extremes by far. And there's been a lot of work showing that a number of record highs are doubling. And so it made some news, but it also sort of expected, and unfortunately not going to see this improve unless something does happen.
Thank you. We have another question for you directed at Jana as well. I said people are very active in asking you questions today, so this is great. With Tropical Storm Elsa had made landfall, it's now working its way up the coast. Can you kind of describe, what this tropical storm can produce when it comes to tornadoes and what people in this area should be on the lookout for regarding weather?
Yeah, so it's very common for landfalling hurricanes and even tropical storms to produce tornadoes, particularly in the outer bands of the system. So not necessarily within the central core where the hurricane or tropical storm winds are strongest, but sort of these outer rain bands where you get a little bit more convective instability developing and you get sort of a smaller area of thunderstorm development. And generally the reason why tropical cyclones will produce tornadoes in the first place is a result of a difference in friction as these bands move from the ocean over land. So when they're over the ocean, they're interacting with a relatively frictionless surface. As soon as they move over land, that bottommost layer of air kind of grinds to a halt to a degree. So you get a sudden sort of deceleration of wind in the lowest, 100 meters or so of the atmosphere as a direct result of the presence of land. And immediately above that, the winds stay very strong, at least for a period of time until everything kind of calibrates and equilibrates. As a result of that increase in very low-level wind shear, these outer wave bands in tropical cyclones do tend to form tornadoes. So that is, moderately common. It's a little less common with a tropical storm than it is with a more intense hurricane, just because the difference in those wind speeds is going to be greater with the hurricane versus the tropical storm. But even just today, we have a tornado watch out for eastern North Carolina as a result of the convection associated with kind of that eastern side of Elsa. So, as far as our area in Ohio, we're generally not impacted by tropical systems very much to begin with, unless it's, something coming up from the Gulf of Mexico that might be, just kind of several days after it had made landfall. So any kind of potential tornado threat that we would have here locally associated with a tropical cyclone is less a result of the tropical cyclone itself and more a result of sort of the underlying conditions that have already been in place. But the tropical cyclone probably is going to act as sort of the catalyst to access those conditions to begin with. So typically tornado events associated with tropical cyclones are confined to, relatively narrow corridors of land that are just immediately onshore from the coast, wherever that particular system is impacting.
Great. And then kind of a follow-up to that we have. Oh, I'm getting more questions in for you both. For a follow-up question for yours, Jana, for people who are interested, we talked earlier about how I've watched multiple, tornado videos on YouTube, and people are out there shooting them, and whether that's tornado chasers who have been trained or those who are just interested. And how can you, what advice do you give for those who are trying to chase storms and tornadoes to be safe while doing so, and what are the best methods to go about that?
Yeah, so first of all, my advice would be, if you have never done it before and you don't have a weather background or an understanding of storm structure, don't do it right away. There are certain rules that we can apply to many storms that allow us as experts to identify areas where tornadoes are going to perhaps form, if a tornado does indeed form. But if it's something that you have really, you're interested in and you want to go out and see a tornado, but you really don't have an understanding of the storm structure and of the sort of logistics involved with storm chasing, then I strongly recommend not doing so. What I would instead recommend is, get connected with a group who do understand and who do know. There are all kinds of like chasecations, they're called. So basically like storm chasers that hire their services out, and people can reserve spots on these chasing trips and go out with people who have experience and who do know what they're doing. When you're actually out there in the field, the weather is just one component of storm chasing. Obviously, it's the drawing component, but there's a lot of other things that you need to consider when you're in chase mode, and you need to think about things, not just the tornado, but you need to consider, large hail, for example. Hail is usually the bigger risk associated with these severe storms producing tornadoes than the tornado themselves. More people's cars get damaged by hail and oftentimes wrecked by hail than they ever do by tornadoes. So that's one thing. You also have to consider if there is a large tornado occurring, there's going to be all kinds of other activity going on. There's going to be emergency responders. There's going to be road closures. There's going to be all kinds of stuff happening. And you need to always be situationally aware when you're out there. And that to really get a full grasp of the multitasking that's involved takes years of experience in doing. I didn't just go out myself the first couple times I chased. I chased with professors of mine as a student, and I had multiple years of doing that, and then multiple years of going out with more experienced chasers than I was, until I felt comfortable to do decision making and take my own students out. So it's exciting, but it's also kind of, I hesitate to encourage people to actually go out and do that. And additionally, the more people you have on the road, the more likely there is to be traffic incidents. If you're chasing through smaller towns, oftentimes there can be, there's a thing called chaser convergence, where there are so many storm chasers out there on the road that you literally have hundreds and sometimes thousands of people pouring into small towns, totally blocking up intersections and things like that. So you can imagine that, if there were a tornado bearing down on an area like that, the traffic that is generated by chasers could actually cause a situation where the tornado could impact the chasers because they are congesting the highways and the roads.
Yeah, that makes total sense. And for all those who are interested in doing this, listen to her advice, because she is the expert here. And for those who are not experienced, that's why YouTube has got some videos so you can experience it or find the resources like Jana had said. We have another question from social media, and this seems like it's more directed towards you, Ryan. Brian is asking, what is the best reply to a skeptic who says the planet has had many climate change events over millions of years? How can humans be responsible?
I would say they're right. First of all, affirm that they have some grounding in science, that we have had many, ice ages and interglacial periods. In fact, if they say that we've been warmer than what we are in present, yes, that's absolutely true. And in fact, we maybe even go back 10,000 years into the Holocene and see that our climate was on average warmer than what it is today. The key distinguishing factor of human influence, there's many, but one thing that's different from this that's unique is that the rate of change is so rapid. We are warming, we're at rapid paces. We are putting greenhouse gases in rapid paces that are basically unprecedented apart from a natural disaster, like a catastrophic event where we have an asteroid impacting the Earth and there's catastrophic loss of life and mass extinction, right? This change we're seeing in temperature, greenhouse gases, ocean circulation, sea ice loss, and ice loss is happening on a blink of an eye in geological timescales. And so the pace is one huge way to determine a human footprint. The other is through scientific experiments run by climate models. Climate models can run and they simulate all the processes in Earth, atmosphere, ocean, ice, land. And they show that only in those climate model simulations, when we include the greenhouse gases as they're changing, only in those simulations do we reproduce the observed trend. If we have the Earth behaving in natural processes without any of these distinguishable human influences from greenhouse gas increases, the climate is relatively steady. We only see major cooling happening after volcanic eruptions. We don't see an upward trend. And so, these scientific experiments that have been done on many different models, many different countries, all giving the same kind of consistent result, show that human footprint with a dedicated experiment, right? So yeah, they're right. It's been many climate changes before. The Earth has even been warmer as recent as 10,000 years. But the key factor is the rate of change, how fast we're getting to where we are, and that climate models conclusively demonstrate that this warming is due to human activity through greenhouse gases, which are related to fossil fuel use.
And can I just add there real quick? I think there tends to be a misconception among the public about what a computer model is. I want to convey that these models aren't just like, little toys that you're building to sort of represent a sort of essence of what we think the atmosphere is or was doing. These are really, really complex. All kinds of interactions are accounted for here. You have water and air interactions, you have land and air, of course, and ice interactions, and basically all the physical processes that occur on the Earth. We've got circulations at the surface of the ocean. We've got deep circulations. It includes everything. It's basically a representation of our Earth to its entirety. So to run these models and to even kind of generate these models has taken decades and decades of work. So where we're at technologically with these models is amazing, even if you compare it just to 10, 20 years ago. They are very, very sophisticated. So oftentimes people are like, oh well, it's just a model. It's how real is it actually? How well does it actually represent our Earth? And the answer is very, very, very well.
Great, thank you. Yeah, I would say that was a great answer, and hopefully our viewer you got a lot out of that you can take and pass on as well. So we're close to out of time, but I do have one last question for the both of you that I would like you to talk on, and that is, can you both, explain and talk a little bit about what you're doing here on Athens campus or with Ohio University students to, help them predict weather or understand climate change and the relation to weather? And just, I know, Ryan, that you work with the Scalia Lab, and Jan, I know you take students out, unfortunately, because of COVID and other matters, hasn't been able to do tornado chase, but can you talk a little bit about, what you're currently doing here at Ohio University?
Yeah, I'll start, and I'll let Jana certainly correct me if it needs to be done. But I would say that we have a really awesome meteorology program here at Ohio University. And so if you're interested in studying meteorology, yeah, definitely check us out. We're a small but strong program. We are a nationally recognized program. We've won awards from the American Meteorological Society. So that's a national organization that kind of oversees meteorology in the U.S. And we've won awards on campus for our community service and outreach and education that we do. One part of that is the Scalia Lab. The Scalia Lab is a publicly accessible forecast website, as well as a hotline. We still dial in every day a weather forecast. So if you're interested in that, you can call that, or you go on scalialab.com. It's linked from our geography page. It's linked from the College of Arts and Sciences webpage, and you can get the weather information there. We issue forecasts every day, including Christmas Day, New Year's Eve, all the holidays, all summer long, and during the semester. It's student-led and student-run. I oversee the kind of big picture of the lab and its function and some of the details. But then students make forecasts. They run the social media accounts that we have, and those are great ways to put out threats. Severe storm warnings, inclement weather that may be affecting the area, and then kind of doing also a case study afterwards and what happened. So definitely follow us on social media. Definitely look at our webpage if you want a detailed forecast that's tailored to the Athens area. I think we're top notch in what we do there. And I also engage students through the sustainability office in my climate and sustainability ambassadors group. So if you're interested, in learning more about that, please feel free to reach out to me. But we're working on and off campus to promote climate literacy and sustainability, and to really just achieve our goals in the climate and sustainability plan earlier than what we set out.
Great, thanks. And for all those listening, when he said to follow it, it is at Scalia Lab Athens on Twitter.
All right, yeah, and I'll take over from here. Just to also kind of, give a little bit of props to our program, and sometimes it's, we don't like to brag necessarily, but Ryan and I are both recipients of the University Professor Award, as well as university-based research awards too. So we have a pretty awesome track record between the two of us. So I think we make a pretty good team. As far as student engagement, oh, and by the way, I always like to throw this in. We're literally polar opposites because he's in the Antarctic. Yeah, fun little pun there.
But good compliments.
Exactly. But yeah, as far as student engagement, as you mentioned, I lead a storm chasing course in non-COVID times when we're actually able to travel and stuff, which is a really, really awesome experience for our students. It tends to be limited to meteorology students or students who have taken some meteorology courses because of the numbers involved, as well as some of the risk involved too. It is a course that is taken for credit, so it's not just like a vacation. So students have to do some work and demonstrate an understanding of the atmosphere, which is why at this point we require meteorology background for these students. But we go out and we are literally at the mercy of the atmosphere for roughly 8 days or so, and I kind of book a period of time and say we're going to go out at some point in time during this window and be ready to go with a 24-hour notice. So we go out and we experience nature, and we actually watch storms as they form. It's a really fantastic learning experience for the students who get to have firsthand experience observing as well as forecasting for storms, and the forecasting aspect is a really key important piece. Students in the classroom, it's kind of a different experience than if you're actually out there seeing the ramifications and the consequences of a good forecast versus a poor forecast, or a good decision versus a bad decision, or in some cases a train that crosses and holds you up for 20 minutes versus a different road choice where you're not delayed for 20 minutes and then you could have actually seen the tornado. These things do happen. So the students get to really learn the ins and outs and understand the nuances and complexities of storm chasing. And I every time students walk away with some kind of really big picture takeaway that they would not have achieved in the classroom. So we really love to get our students engaged. We are both really invested in our students' success and care very much about that. We have multiple opportunities for graduate work as well as undergraduate research, which is kind of unique to us. Sometimes larger institutions tend to kind of blow off the undergraduate research experiences and instead focus much more on graduate experiences. So we really like to invest in our undergrad students as well.
Great. Well, thank you both so much for sitting down and talking with me this morning. Our viewers had great questions, and you gave such great answers and information to all of us. And I know I learned a lot that I've been jotting down notes to go forward with. And so I hope that all those who watched also got that and some information to take away. So thank you both again so much. And for our viewers, if you have any other questions that you would like to ask Ryan or Jana, please feel free to comment those, direct message those to us, and we will send those to them and get responses for you. So thank you again, and I hope you have a good rest of your day, and that the weather outside treats us pretty fairly, and we'll be looking to the Scalia Lab to let us know what that looks like, I guess.
Thanks so much, Sam.
Thank you both again. Take care.
All right. Bye-bye.